Okay, so let's get started. So welcome everyone to this lecture today. So what we will do today is, or what is left to do from last time is, we still had to complete the proof of theorem 2.2, and there the only thing that was missing was the proof of lemma 2.5. And yeah, so that will take us like maybe the first half, and then in the second half I'll start going to this new topic towards stochastic analysis, where you filled in the questionnaire. Okay, so yeah, maybe just to recall, so theorem 2.2 was this statement which showed us that if we have two Wigner matrices that match up to fourth order, then their local k-point correlation functions will be the same in the bulk. And last time we proved the screen function comparison statement, which was one part of the proof. And then the second part is this removal of the smearing out. So remember, we were looking at functions f when integrated against the local, well, here 2-point, but in general k-point intensity measures. And but for the proof of this screen function comparison, it was better to have these more, in some sense, more smooth or more explicit smeared out versions, f eta tilde. And now what this lemma 2.5 says, that in the initial statement we can easily replace f by f eta tilde, because the error that we make by this replacement is small. Okay, so just to recall the complete setup. So E is an energy in the bulk. We have some epsilon, which gives us the scale we are looking at, and then we have a function f. A C1 function with compact support on R2, and the f eta tilde is the following smeared out version. So we take the convolution. We take the convolution of f in both coordinates with these functions theta eta tilde, which is defined as follows. It's the imaginary part of this ratio here, which you recognize from the Stieltjes transform. So this looks as follows. So that's somewhat an approximate delta function on the scale eta. And yeah, so we smear these out, and then the goal is to compare that if I integrate the difference of f and f eta tilde for this choice of eta tilde, then if I integrate this difference against the local 2-point intensity measure of a Wigner matrix H at this energy E at the bulk, then I get something that is small, that goes to 0 when n goes to infinity, and that will be the last step in the proof, of theorem 2.2. Okay, and now to proceed. So maybe now is a good time for you to take a picture if you haven't done so yet. But so far we only recorded things from the last time, and so now what we will do next, of course, we have to go into the proof, and the first thing will be to actually use the definitions. So now this is the proof of lemma 2.5, and the first thing we want to do, we use the definitions of rho, and then rewrite it back as an expectation of some function of the eigenvalues. So I can just use by the definitions of, now I have the local k-point intensity measure, and then the k-point intensity measure. Recall that the local k-point intensity measure was a shifted and rescaled version of the standard intensity measure. So because of that, we have the following identity. So if I have the difference of f and f eta tilde evaluated at u1, u2, and integrated against the k-point intensity measure, then well, there was some rescaling. So maybe I first give you the result, and then I explain how it emerges. of lambda E minus E in rho of E lambda J minus E. Okay, so how does this come up? So first of all, these rescalings here, they come by the definition, they come in from the definition of the local K point, the local K point intensity measure as a push forward measure under this map from the K point from the K point or 2-point intensity measure. And then the 2-point intensity measure was defined as this expectation of the sum over distinct indices. So this now we just have 2, so I and J are different. And then here's the observable that you had F, and then you evaluated that at these 2 arguments. And now we will look here at 2 different regimes when for this function, for this sum here. But first we will choose, so we can fix a xi, which has to lie, say, in 0 and epsilon over 4. And then we define a zeta to be the n into the xi. And we look at the following event. So that's actually will be an event that occurs with high probability, as we will see later. So that's namely the event where all eigenvalues, if I shift them, around E, or center them around E, and then I rescale with the typical eigenvalue spacing. And then this looks like this. It should be bounded by I minus I0 up to some error term for all I running from 1 up to n. Okay, so that's the event, and that's the event we want to look at. And now I want to smuggle this event in here. So well, maybe I write consider the event and decompose. Now we take this expectation and decompose it into 2 parts. F eta, and now we smuggle in the this event.
I'm sorry, what is I0 here?
Yes, sorry, this I have to still fix. Good question. So we consider the event for some I0 and some well, maybe it's better like this. Okay, I hope this is not too messy now. So the I0 and also the C, they will be fixed in a minute when when we will apply the eigenvalue rigidity to show that this occurs with high probability. I hope there are not more confusing things here anymore. And but first I want to smuggle in this event into the definition here. So I will write this as I plus I C and now I have these things with the characteristic function and without. So this should be the characteristic function 1c times this event. So let's copy this now. Paste. And then we have the same thing with the IC, but then we have the complement. So I have a IC here, and then I have this complement here. Okay, so we have this decomposition. Yeah, maybe you can take a picture now, and yeah, and then of course we will show that both of them are small, so that I is small and IC is small. That's what in the end what we have to prove. And I hope the notation is clear now. If there's still something unclear, then please ask. And we will prove now that both of them are small. And first we want to show that this event, if the I0 and the C are chosen properly, then this event occurs with high probability. And to that end we will use the eigenvalue rigidity. So owing to eigenvalue rigidity, so that we proved last semester, and I recall this as theorem 1.3 in this lecture, in this course. Because of that, yeah, just to recall it, maybe it has been a while, some of you have forgotten. So this is, well, stochastically dominated, but I just want to smuggle in some delta. I minimum n plus 1 minus I to the minus 1/3. And yeah, the gammas were defined as the quantiles of the semicircle density. We have maybe for any delta, we have this with very high probability. And it holds for all I, for all indices of eigenvalues, right? And yeah, because of that, hence we find I0 in 1n and C bigger than 0, such that, well, I said it holds with very high probability, but actually for our purpose it will be enough to use that the probability as at most n to the minus 1/3, the n to the minus 3, and so we find such I0 and C, and here I used something else, namely I have to use that these quantiles gamma I and gamma J, they are bigger than maybe some C tilde n to the minus 1, their distance if they are different. So for all I and J. Yeah. Okay, so just to recall, so why is this correct? So what we want to prove is that this here is a small probability, but we know that lambda I and gamma I, they are very close to each other. And we can also find, because the gamma i's get very dense for large n, we find an I0 such that this gamma I0 is close to E, and then we can just plug in this definition, and then we have to allow for some error term. Okay, so we know now that that event Xi happens with high probability, and now we already have this estimate, and then what we can immediately do is we can immediately estimate from this the IC. That's because of the following. So thus IC is of order n to the -1. Why is that? Because F and also, well, maybe I just write like this, F and F eta tilde are bounded, right? There, F is a smooth function with compact support, so that's bounded. And then F tilde is this convolution, but you can easily convince yourself that that's also bounded. And maybe I should just say a word about why this is correct. So, well, we now know that this here has probability n to the -3, and this sum here, so it's these two things are bounded, so each summand here is bounded, and we have a sum over n squared terms, so we can easily estimate this here from above by n squared times the probability of this event, and because of this we get that the IC is at most order n to the -1. Okay, so that was the first part, and now now we continue with estimating the I. So we now estimate I, and then we use that F has compact support to decompose this difference F minus F tilde F eta tilde in two ways, or in a way, and then we will have a decomposition into several terms that we can easily estimate. As compact support, so support is say in a large ball in R2, and the zeta is some n to the Xi, so that's large. So because of that, we have the following decomposition. Well, I guess I can still fit in one line. So I take this difference here, and then I decompose it into 4 terms. So there's F smaller equal smaller equal. Then there's an F smaller equal bigger. Then there's the opposite, so F bigger smaller equal U1 U2. And last but not least, bigger bigger. Okay. And yeah, now we have this for large enough n, and for all. And there I have to tell you what these 4 functions are. So maybe, well, now is maybe a good time to take another picture. You want to do that. And now I give you the definitions, and basically the definition will always be that I decompose it into the regime when the U is small, or the U is U1 and U2 are small or big. So you will see what it looks like. So I have an F minus F tilde of U1 U2 when the U's are smaller than my zeta, smaller equal zeta, and U2 smaller than zeta, and now the others are obviously the other way around. So U1 U2 then I get here that the U1 is smaller than zeta, and the U2 is smaller, and the U2 is bigger than zeta. And now here's a difference, because now if one of the arguments is large, then I don't have to, if at least one of the arguments is large, then I don't have to consider the f anymore, because f has this property that it has compact support, and the zeta is something that goes to infinity with large n. So if I take n to be sufficiently large, then the argument will be outside of the support of f, so that contribution will vanish. So, and then I have the other two. So now the U1 is big, and U2 is not too big. And then maybe the last one I can just copy. So then, of course, for the last one, we will have that that now both arguments are big. Okay. So yeah, I guess this is pretty much obvious how this works. And okay, so now we have this decomposition, and then we will just estimate these things. Okay, and yeah, maybe first I should quickly recall how the yeah, let's just recall how the f eta tilde was defined. So yeah, as we've seen it just before, it was the convolution of f with these kernels. So ui u2 v2, and now we use that these kernels are normalized. So the theta eta x dx is 1. If I integrate it over all of r for all eta, we get the following. So yeah, maybe you can take another picture now, and then and now I want to estimate this difference. And the point here is that I will just smuggle in. So they are evaluated in u1, v1. And now I just smuggle in everything into the argument, ev1 f of u1, u2 minus f of v1, v2. No absolute value yet. And then I have these two thetas, 1 v1, u2 v2. Okay, and now I use that f is bounded in Lipschitz. So then I can take bounded and Lipschitz. So then I can take this, estimate this difference here very easily. So that means that if I take the absolute value of this, then this is smaller than constant times v1, v2. And then here I get the minimum. So if the difference between u1, u2, u1, v1 and u2, v2 is small, then I use the Lipschitz continuity. If it's big, I use the boundedness, and these kernels are anyways positive, the thetas. Okay, and yeah, now I can, well, I can put these guys here inside, and then distinguish. Then if I get the u's together, the u1 minus v1 close to this here, then I will estimate them together. The other one I'll just integrate out, And yeah, for the constant here, it's even easier. So that means if you think about it for a second, it looks like this. I have a dx integral, then I have a minimum over x and 1, and a theta eta of x, right? So just go through it. So I pull these two things in here, and well, of course, in there, and for similar here. And then I can always integrate out one variable, and for the other one, I get the, so I can, so for example, with this term here, I get both thetas, then I can integrate out the v2 variable, and then I get this. And then for the other guy here, I get the same sum. And yeah, you can do this integral here, and then what you get is that this is order eta tilde log eta tilde. I see, well, maybe, well, we still have some space. And then maybe I just give you how this follows. You just use these two integrals. So you just distinguish these two cases where the minimum is x or where the minimum is 1. And then you integrate out what's left over. So yeah, maybe I just write this here. So this will be order eta log eta, and the remaining integral is just bounded. And 1 infinity eta x eta dx, this is order 1. And then because of our choice of eta, this is the big term. In the order 1 term we can forget. So this is really what we end up with. So in total, I get that the f u1 u2, this is smaller than, this is of order eta tilde log eta tilde, and then I keep the characteristic functions. They will be useful later. Okay, so yeah, maybe now is a good time for another picture. And then the next thing we will do is we have to estimate. We have to estimate the other terms, and this is maybe a little bit more complicated. So so how does this look? We again estimate the argument. Now we only have one argument left. So so what we are left with is, so we have to estimate something of the type f eta tilde u1 u2 characteristic function u1 bigger than beta. So that's the thing we have to estimate, and then we do it as follows. So yeah, we just plug in the definitions, and so 2 pi squared, and then here I have the eta tilde u1 v1 eta tilde squared, and then the same guy with u2 and v2. And now how we estimate this is, this goes as follows. So maybe I first, well, I'll give you the result. So this is again the characteristic function, and then eta tilde u2 squared. So how does this come in? So well, what we can always do is we can always integrate out the v2 and use that the f is bounded, and yeah. is bounded and has compact support. So if we integrate out this V2, then okay, let's do it as follows. So we first estimate f as a function with compact and bounded support. So both of these integrals will go over a compact interval. And then I can integrate this here out. So this gives me some bounded, some multiplication with a constant. And then what I'm left with is integrating this here over a bounded area where I know that the U1 is very big. So then I can just estimate this here by this ratio here, this ratio, and then the V1 will not play a role because this is bounded, and the U1 is at least zeta. So remember that has this n to the eta. So this here is at least U2. This difference here is at least absolute in modulus absolute zeta over 2, say. Okay. So then in this denominator here, I can also forget about the other term here. So I just left with this ratio. This will be an integral over a bounded domain, and the f is also bounded. So there's nothing nothing happening. Well, maybe I'll give you a short explanation here that you have to integrate out V2 and use that f is bounded and has compact support, and that in particular implies that the U2 minus V2 squared is bigger than, say, 1/4 U1 squared, as U1 is bigger than zeta. Okay, and just to make it a bit more, bring it in a little bit nicer form, we can use this definition again and then change the denominator here a little bit. Namely, this is the same as order characteristic function U1 bigger than zeta, eta tilde U1 squared plus zeta squared. So this looks now like a bit overcomplicating this because I'm writing the error term in this way, but actually it will make my life a bit easier in the next step. So maybe just to conclude from this, what we learn about the f. From this estimate, we get some information about these other f's. So if you look at the definitions, I get that f bigger, smaller equal is therefore of order eta tilde U1 squared plus zeta squared. And then I have these two characteristic functions. So U1 is big and U2 is not too big. And then I have this, well, the very same thing holds, of course, for the smaller equal bigger. That's eta tilde U1 U2 squared zeta squared. Now the U1 is not too big and the U2 is big. And then the same thing is, the square of this if both of them are big. So then I have an eta squared U1 squared zeta squared U2 squared zeta squared tilde, and both of them are big. Okay, so I have these three estimates, and then I define these e's. And now I want to so maybe you can take another picture right now, and then we can go back and see how this definition on the this decomposition of the f, how you can use this to decompose the I. So remember, we had this this decomposition here of this difference, and then I want to plug this decomposition back into the definition of the I, right? So now we cannot gain from this, but we have to estimate all of these terms individually. But well, we will of course use the definition here. Okay, so well, we decompose I being I smaller, smaller, I bigger, smaller, plus I smaller, bigger, plus I bigger, bigger. According to the decomposition when we had the difference of the f's, there was f smaller, smaller, plus f bigger, smaller, plus f smaller, bigger, plus f bigger, bigger. Okay, so I guess it's clear how these things are defined. And yeah, now we have to use again. So yeah, what remains is showing that each of these i's is of the order n to the minus c, right? Okay, and so let's recall the definition. The definition of zeta, sorry, the definition of the event xi. So that event was defined as follows. So it gave us a lower bound on these differences in terms of I minus I0 for one fixed I0, and there was some error term here. Okay, and now these characteristic functions for the U1 and the U2 in the definition of the f's will come in handy, and they will look at, but first we use this definition to estimate how many of these terms we actually have. So by definition of xi, we have the following. I take the characteristic function and then I sum up over all eigenvalues such that in their rescaling they are smaller than the zeta. Well, maybe I write it like this. So the absolute value of this rescaled variable is smaller than zeta. If you think about this for a second, then this gives you that they're of order zeta, just by the very definition. So what does this tell me? So this is somehow the number, and this I will actually call sharp, and then yeah, somehow this here is the well, I guess it's pretty clear number of eigenvalues lambda I, such that this difference is smaller than zeta. So that's what we will use in when estimating these characteristic functions or this f's. Okay, so that will be an important ingredient, and then we can just directly estimate from this and the definition of and the estimates on the f's. We immediately get estimates on the i's. So how is that? So we get that the I smaller or smaller. Well, how would that look like? So, well, this is, let's go back to the definition. So I'm now in this situation here, and now I sum up over all, I sum up over all I and j, where this part here is replaced by the f, capital F, smaller, smaller. So here I get the number of all, well, one of these sums, now both of these sums are smaller, so each of these sum will give me, together with the characteristic function, will give me a zeta. And then we anyway set an estimate on each of the terms. So I get from the estimate, I get that this is zeta squared times, and then eta tilde log eta tilde, right? So here it's where we used star and hash and the estimate on the f smaller equal. And well, now we can plug in everything. So this is n to the 2 xi, n to the minus epsilon log n to the minus epsilon. Then I can use the choice that the xi is smaller than epsilon over 4. So I get that this is order, well, n to the 2 xi minus 4 xi, and then there's a log n, and this is clearly of order n to the minus xi. Okay, so that was the first part, the first of these things. Then if I have an I bigger, smaller or equal, then I can do the following. I can, again, for one of the variables, I can use this sharp, and for the other one, I use that the UI is big, so I get something which I can gain from, and the definition of xi. So let's see how this, what I end up with. So I get a zeta from estimating the U2, and then what I'm left with is another sum over eta tilde divided by I minus I0 squared plus zeta squared. Okay, and well, I can just sum up these things. There's of course a problem when the I is equal to I0, then I have to do something else. This term I take separately, but the other terms, they will be small. So this is order eta tilde over zeta plus, and then zeta eta tilde, and then I have the sum over I in z without 0, 1 over I squared. That's a finite sum. So this is of order eta. If something is not readable, please interrupt me. Eta tilde times zeta, and then if you check it, this is also order n to the minus xi. And yeah, just to conclude, the other terms are of course similarly, well, there is actually exactly the same. We see that I smaller equal bigger and I bigger are sufficiently small, and that completes the proof. Okay, I'm not sure how far you took a picture, so maybe you can take another picture here. which concludes the proof. So yeah, the point here was that we can use the number of eigenvalues that are small. We can use for those parts where they are smaller equal, and where they are bigger, then we can just sum up. Can sum up these because we are on the event Xi. Okay, and yeah, if there are no more questions, then this answers this completes the proof of this lemma 2.5. So which also then completes the full proof of theorem 2.2. And then after the break, I will just give you some remarks about this, about some possible generalization of this theorem 2.2, and then we will start with a new topic. So if there are no more questions, then I would say we can continue at 10:15. Okay, I hope you're all back. So then maybe let's continue. So yeah, we now completed the proof of this of lemma 2.5, which was also then the last missing piece in the proof of theorem 2.2. So that completes this section. And I just want to close it by a few remarks, namely that one can actually relax this condition of having 4 matching moments, and also it's applicable to other setups as well. So yeah, these are just some remarks for you so that you can maybe get a better overview over these kind of arguments. So theorem 2.2 remains correct, and also one does not have to change the proof drastically. So the in fact, the proof just needs some simple adjustments. So same proof with simple adjustments. If one looks at the following condition, if so one replaces the condition that one has 4 moments, so of course one has to keep that everything is a Wigner matrix, or that H and H prime are Wigner matrices. So instead of assuming that H and H prime match to order 4, we require the following condition, which is strictly weaker, that we find a delta positive such that if I still have to take these kind of mixed moments of entries and compare this with the entries of the other matrix. But the important point here is that we can allow for an error term the following order n to the -2, while then actually it essentially does not matter what's on the diagonal. Yeah, we just need that the error term is a bit smaller than n to the -2, and this comes in as follows, namely if you look at the this only comes in the proof of the screen function comparison statement, and there this moment matching condition was used to see that the definition of the A is independent of whether one has an H or an H prime, and if you go to this proof, then you see that at this point you'll see that this is such an error you can still allow. So such an error is in the definition of A still up to a small error term. This gives the same definition of the A, but this size of the error term will still be affordable. Okay, so I don't want to go more into details here, and I should mention, of course, that the K and the L have to be smaller than 4, and this has to be true for all I and J. indices of the matrix. Okay, and then one can use this method also for the spectral edge. So far the E was always inside the bulk, so between -2 and 2, but one can also choose it to be ±2. And the argument is somewhat, and I mean, at least the basic ideas are similar, and that's what I want to mention in the second remark. So the green function comparison method can be used to show universality. And then I just want to mention two cases here. So the first one is at active spectral edges. So that's when the E would be ±2. Then of course you don't get the sine kernel anymore, or the analog in the GUE case, but something else. For the K-point correlation function, maybe also interesting is to look at the distribution of the following guy. So know that the largest eigenvalue converges to -2, and from the eigenvalue rigidity, we would expect that it fluctuates on a scale n to the -2/3. So if I rescale the largest eigenvalue in that way, then I should get an order 1 random variable, ideally, in the limit when n goes to infinity, and that's actually the case. This we will see now in the next weeks. And another thing which we won't have time to discuss in these lectures or in this course, you can also look at eigenvectors. And there you can, for example, look at the distribution of a k-tuple of eigenvectors or components of eigenvectors. So e.g. Distribution of x I1 k1 up to x IL KL, so it's not a k-tuple but an L-tuple, and there I use the following. So xik is the rescaled entry of an eigenvector, and u1 un are eigenvectors with components. So ui has components uik. Okay, running from 1 up to n. Okay. So yeah, maybe it's maybe the end of this section, so you can take another picture. And yeah, maybe I should give you some overview. So the next part, first we need to introduce some new techniques and some new methods. This goes to the stochastic analysis questions and then stochastic analysis tools. But then we want to study this spectral. So yeah, in particular the distribution of the largest eigenvalue. And well, if we have time, then maybe we also see this green function comparison method coming up again there. I will definitely state the theorem. Maybe I'll have time to prove it to apply it to this distribution. So maybe there's a distribution of. Okay, so yeah, as I already announced now a few times, we now will go to this new set of tools. Maybe some of you have already seen parts of it, but I'll try to introduce it. So yeah, maybe I should start a new section that's now called stochastic analysis of random matrices. And And yeah, although it's maybe, and then I think it's the best to start with some kind of explanation why we will need this and how it will be useful. And yeah, let's do that. This order is maybe not the best to produce good homework exercises, but I think it's better to give you an idea first why we need to do this and what we will use it for before we go into before we go through the definitions. And I'll try to be to start quite basic. I will not prove any results about in stochastic analysis that's not really tailored to random matrices, but I just list the tools and the definitions that we will need. Okay, and yeah, the overarching goal now will be that that we want to understand universality for larger families of matrices, and yeah, for us it will always be Wigner matrices. So extend universality results to larger families. Random matrices, and yeah, maybe the thing you should have in mind is that for us we try to understand Wigner matrices, but where we don't have this four-moment Wigner matrices that do not match to order 4. That do not match to order 4. Okay, and there's a very powerful approach, which is called the 3-step strategy. Most powerful approach. The 3-step strategy, which is mostly due to Erdős and Yau and their collaborators Schlein, Yin, and Bogart, and many others have also contributed to this, and this is still a very active topic of research. And it started roughly like maybe 10 years ago. And then there were this method allowed them to prove actually these kind of universality results that we've seen now without this 4-moment matching assumptions, and that was kind of a big breakthrough. And yeah, I guess we will here assume that. So now I first want to describe it a bit, and we'll just concentrate on when it's a Wigner matrices, you can actually, when H is a Wigner matrix, you can actually relax it quite a bit. You can allow for, well, having different variances, having expectations, and then also you can drop the assumption of having independent entries, but that goes much further. So we first want to look at it in the most simplest case, and the first step is somewhat what we've done last semester. So the first step here goes under the you have to understand the behavior of eigenvalues above the scale of eigenvector. Well, maybe better on all scales. All scales slightly above the typical eigenvalue spacing. So yeah, that's what in particular eigenvalue rigidity and the local law are here the key ingredients. Eigenvalue behavior on all scales slightly above the typical eigenvalue spacing. So yeah, that's what we've seen as eigenvalue rigidity, and also in some sense, that's all the local law, which is the main tool there. So that was roughly what we've done last semester. Then the second step is that you want to understand the universality for matrices which have a Gaussian component, and this component should be, as in some sense, as small as possible. And here you can imagine that if I have a matrix which has a very big component, then it should, in some sense, well, first of all, if this component is very, very big, so you have a very big GUE component, then you've seen, well, there we have somewhat other tools, and these are also applicable if you have a not too big other Gaussian component. So in some sense, it should be easier as long as you have more Gaussianity. It should be easier to prove universality, and in some sense, that's the main tool here. So you want to understand universality for the following matrices. So I will call them HT. And T somewhat describes how big the Gaussian component is in some sense. So with a small, so ideally T is small, small Gaussian component. In the matrix, yeah, well, you can think of it first to look as follows. So we have some H0, which is just some Wigner matrix, and then we add to it a GOE or GUE. So where T is sufficiently large, so that's somewhat that should be the philosophy, that of course if the T is 0, you have H0 and then you don't know anything, but as soon as you have some small Gaussian contribution, then the hope is that then everything becomes better. So so yeah, beta is 1 or 2 here, and H1 is GOE, usual convention, and H2 is GUE, and H0 should just be some Wigner matrix. Okay, so yeah, as I said, the hope here is that if you have a sufficiently big Gaussian component, then you can show that your eigenvalues behave in some sense, or are very close to behave like the eigenvalues of a Gaussian matrix. So that's what we would expect for universality. And then the hope is that somehow you can go back with these, that once you understand this HT for some kind of small t, you can also say something about H0. And that's actually correct in the following way. Well, you cannot directly say something about H0, but if you start from a matrix H and you choose your H0 cleverly, or yeah, suitably, then you can actually achieve that the HT is sufficiently close in this moment sense to H, such that you can compare the things. So that's somehow the third step. So then you can use green function comparison for H and HT, and yeah, as I said, the H0 has to be suitably chosen. For suitably chosen H0. Okay, so maybe it's good to draw a picture for this. So yeah, I mean, in some sense, we already also did the third step now. Well, there will be, we will not manage to get 4-moment matching, but then the 4th moment will be a small perturbation. And so essentially, we already did the third step. So what we will do now, or we will look at the second step. But first, I want to give you some, maybe some graphical. Yeah, maybe now is a good time to take a picture. And then I want to explain, or well, give you some picture which in some sense encodes these 3 steps, or at least the second and the third step, so that you have something in mind that you can, yeah, that you can relate to, that you can keep in mind. So maybe graphical idea for 2 and 3. So let's look at the space of random matrices in some sense. So maybe that's the whole space here. Space. Random matrices, and yeah, for now I always think of emission or well, real symmetric or complex emission. And imagine we want to understand this matrix H, which lies somewhere here in the middle. Then we know that we can do this 4-moment matching. And then we see that we will have the same universality. So that's somehow some submanifold here, if you want to think of it that way. So maybe I write here, so matching H to order 4, and then one can believe somehow that that's the same universality class. This is of course not completely precise. We have not proven this yet. Same universality class, but then one can use something like this green function comparison. Okay, so that's somehow what we understand, and then we have this kind of Gaussian flow, yeah, which somewhat also lives in the space. Maybe let me draw it like with blue lines here. So, well, maybe it's a bit nicer if I draw it like this. So, well, because you can imagine, of course, if the t goes to infinity, then everything converges somewhat to this h beta. So I want to draw this flow like this, maybe. So this is the flow ht, and now the idea would be that if we can construct a nice matrix H0 such that we get close to this, such that the flow runs for a little bit of time, so that by the second step we get universality. So we choose a H0 here such that the HT, such that for some time we run it for some time t, then we get universality for such matrix, and then we are already close to the H. So that's somehow the idea that we have. So we have an H0 here, and then we get some HT maybe close by here. I hope this is visible. And then the time should be sufficiently large, and we should be sufficiently close to H so that we can compare these two things. Okay. So yeah, that's somewhat the very rough idea. Of course, so far this is mostly blah blah, and we have to prove something and make it precise. But what is clear is now that so yeah, maybe I should remark that 1 and 2 we have so far already looked at. What we have done so far, done in some generality, is 1 and 3. And yeah, it was also important that in some sense the local law here is the main input for 2 and 3. Well, at least for 3 it was an important input for this green function comparison. We use the local law directly, so various estimates on the green function, some control on all entries of the green function, and we also use rigidity, and also the local law will be an input for the second step. So what remains is somehow this 2. That's what we want to look at now, and then we have to analyze how these eigenvalues evolve under this flow ht, and in particular we have to analyze them for somewhat large t. I guess that's the so that is, we have to analyze distribution of the eigenvalues, well, or their distributions. Another flow HT. So meaning that when we add, T becomes larger, then we add more and more Gaussianity. And okay, so I give this a star, and yeah, can maybe take another picture. And the best tool to do these things is in some sense, so you add some independent randomness. So yeah, maybe I should have remarked that, of course, we want the H beta to be independent of H0. So we, in some sense, add additional randomness to the picture. And the best way to analyze then now the HT, so how the eigenvalues evolve under this flow, that will be stochastic. Yeah, that will be stochastic calculus, and we will have some stochastic differential equations. And I first want to, without defining what it means, I will give you the equations that we want to look at, and then I will introduce the things that we will need and define how everything, how this is studied mathematically rigorously. And this I'll start today, and yeah, well, maybe I will not have enough time to go through everything, but at least we will start with the most important definition. So yeah, we will look at stochastic calculus and then stochastic differential equations. Okay, and the two things, or the two basic equations we want to look at are the following. So, well, in some sense, instead of star, we want to study the following. We will study the solution of the following equation. So the matrix flow HT comes as follows. So you will add to it, you will have a term which is a matrix Brownian motion, and then it should come in the appropriate way. So it's in some sense a GOE Gaussian Brownian motion, or a GOE Gaussian GUE Brownian motion, or a GOE Brownian motion. And then there's another drift term, which is it's added for convenience, because that will mean that HT will stay a Wigner matrix if you started from a Wigner matrix. So this will be a appropriate matrix valued Brownian motion term. So diffusion term valued Brownian motion. And yeah, the advantage is that compared to star is that the HT is a Wigner matrix if H0 is a Wigner matrix. So that's somehow a flow which lives on the space of Wigner matrices. And then there's an interesting, well, of course, a much more complicated evolution on the eigenvalue level. So the eigenvalues well, I want to call them lambda 1t up to lambda nt of ht. they evolve according to the following law. So yeah, there's some constant factor. Then I have a standard Brownian motion. And then I have a drift term, which is a function of the eigenvalues. But the interesting thing is that it only the eigenvalues show up and not the eigenvectors. So lambda I minus lambda j, and then dt. Okay, yeah. So this is a standard Brownian motion. So according to, yeah, of course, this is a consensus system. And yeah, here we have then standard Brownian motions. But as I said, I will define all of this. I just want to give you an idea of what kind of equation we want to look at. And yeah, this will also come later. So the solution of this lambda, yeah, such a family here, or solution of this type of equation is called Dyson-Brownian motion. So it's some kind of special type of yeah, Brownian motion and the solution there. And in fact, all of these will be formulated as kind of integral equations. That's the natural formalism for this. These are stochastic differential equations, which have this Brownian motion randomness term. And this is what I'll explain to, or start explaining or introducing next. So yeah, as I said, I will only give definitions. So yeah, maybe now is a good time for a picture. So this was just to indicate what kind of yeah, objects we want to study or equations we have to analyze. And now I'll properly define what all of these things mean. And yeah, I'll according to your, so maybe I start a new page. So according to this questionnaire, there was somewhat a very mixed background. So I tried to introduce or at least give all the definitions we need from stochastic calculus and stochastic processes. And of course, if something is unclear, so you can ask me, we can discuss it maybe also separately. And yeah, maybe I'll start a bit too boring in the beginning, but I just want to make sure that everyone is on the same page. And I'll only give definitions and theorems, a few examples, some things we will also discuss in the homework. And yeah, and then proofs, if you're interested, I can give you references. There's a book, for example, by Oxendahl. Maybe I can put it on the Moodle page, which is a good introduction, and I guess that's also what I'm mostly using. And for the beginning, I want to start with stochastic processes and Brownian motion, and yeah, also martingales. So define what all of these things mean. And yeah, so I guess maybe most of you have seen what a stochastic process is. I just want to recall it and maybe also give you a little bit of intuition. So stochastic process yeah, is a family. So you just have a collection of random variables which are indexed by some set t. And the random variables all live on the same probability space. Omega or sigma algebra f, and sorry, and the probability measure will be, I will denote by this p. Suppose there's p. Okay. Yeah. Then maybe I should mention it with some index set t. Okay. And there are some usual examples. So usually I have that the xt has values in Rn, and the t is one of the following guys. So the t is either maybe the natural numbers, so the positive integers, the positive half line, or an interval. So these are the most common things. And then you can there are two basic operations, and you can fix a t in the set t, and then by definition you get the random variable, which looks as follows. You map an omega in the space omega to xt of omega. So this is gives you a random variable. That's somewhat clear. But then you can also do the opposite. So you can fix an omega, and then you look what happens if I let t evolve. So maybe t. So I can map the little t, which comes from the set capital T. I can map it to the xt for fixed omega, and then this is what we would call a path. So this is maybe I say it's called a path. So in some sense, you see how something evolves according to this stochastic process. And then maybe a helpful intuition is maybe this is I still have a bit of space. So the intuition could be that that t is a time variable, and the omega is some, maybe a particle or an experiment. So you let something run for some time, or you have a whole bunch of particles that have different starting conditions, or that have a random starting condition, and then you let them evolve according to this stochastic process. Okay, and so maybe it's a good time for a picture now. And then the last thing I want to say is what it means that the stochastic process is continuous. It means that it means that this path are continuous functions, right? So if t is we say that because I need that the t has some metric structure, and also the range of the random variables, but this I want to assume now. So, and we say it's continuous if the probability when I take all omegas and look at these paths, when this is continuous. Okay, so I look at the event where the path is continuous, and this should have probability 1. So almost surely you should have a continuous path. I should say that there are various kinds of subtleties here, which I don't want to go into, because of course a priori this set is not measurable, because if your set t is something uncountable, which is if the index set t is uncountable, that's of course the only time when this is an interesting question. Then it's not at all clear that this event is at all measurable, and then one needs to go to have a complete sigma field. And but you can always complete it, and I don't want to go into these details now, and we will not need it for the course. But I just want to warn you, and if you're interested, then of course there are various sources you can look at. And then maybe the most important stochastic process is the Brownian motion that I've now already mentioned a few times. And it's a stochastic process on the positive half line, or the time variable, so to say, runs over the positive half line. and it will have values in Rn. And such a process is called Brownian motion if the following conditions are satisfied. And yeah, well, obviously Brownian motion on Rn. And we'll have 4 conditions. One, so the B, I want it to start at 0, so the B0 should be 0 almost surely. Then the second is that B, well, yeah, B has independent increments. We'll define what this means. Increments. So that means that for all positive t, well, no, can also be 0. For all non-negative t and u, we have that if I take the Brownian motion at time, I mean, in the sense of Brownian motion, the t will always be thought of as a time. I take the Brownian motion at t plus u, and I subtract the Brownian motion at t, then this is independent of everything that happened before t. So in some sense, this sense you restart the Brownian motion. So it's independent of Bs for s smaller than t. Okay, so this is somewhat, this difference here is what is meant with an increment, and the increment is independent of everything that happened before. So yeah, maybe more formally, independent of this, and this means that I look at the sigma algebra, which is generated by the Bs for all s smaller than t, or sigma field. Okay, so that's the second condition. There, the third and the fourth. Namely, I want to have that the distributions are Gaussian. So this increment, or the distribution of increments is Gaussian, and that also means that the increments of the that the BTs itself are Gaussian. This is Gaussian, so well, Gaussian distribution with mean 0 and variance u. And then the fourth condition is that B is continuous. So almost surely all paths are continuous. And yeah, so maybe I should explain why it's called Brownian motion. So this is supposed to model the motion of a pollen which is suspended in some let's say water. So then the B describes the location of the pollen. So now you could think of an Rn dimensional situation, and all of Rn is water. You put the pollen at the origin, so you start with the location B0 equal to 0, and then the pollen evolves, and then all of these conditions are quite natural. So of course you want that each time the pollen moves, it should have a continuous, it should follow a continuous movement. The increments are independent, so once it has moved after a time, it's the same as if you would start at this time again. So that's what it means, that, and in particular, it should be independent of what happened before. And you always expect that the movement follows a Gaussian distribution. And then let me, maybe is another good time for a picture. And then the Brownian motion is also a prime example for a class of stochastic processes, namely martingales, that I want to define next. But first, I need to explain to you what it means that to have a filtration. So filtration on a measurable space that is a family of sigma subfields. Sigma subfields Ft, which is a subset of the big guy F, such that the following holds, such that if I have an S smaller than T, then the Fs is contained in Ft. So it's an increasing family of sigma algebras and of sigma fields. And yeah, maybe I should have put in the Ft here, so the T is now a positive real number. And yeah, I guess you know from probability theory that the sigma subfield gives you some kind of information. So in some sense, filtration means that with time you gain more and more information about about the object you're analyzing, or in particular about the stochastic process. And now with this definition, I can define what a stochastic process is. What the martingale is. So I start from a stochastic process X, and it's called a martingale. And the martingale is always with respect to some filtration, with respect to the filtration Ft, if the following three conditions are satisfied. So first I need that Xt is Ft measurable for all positive T or non-negative T. Then I need that it's Xt is integrable. So the expectation of Xt absolute value is finite for all T. And then these are in some sense technical conditions. And then the most important condition is that if I take the expectation of Xt with respect to the sigma field Fs, then I get Xs whenever the T is bigger than S. So what does that mean? Well, it means that whatever information Xt carries, or you want to know the expectation of Xt based on the information you have at Fs, then all of this information is already contained in Xs. So in some sense, so in that sense, all information of Xt, the expectation, if you only know Fs, then Xt looks like Fs. So that's what this means. And then maybe to conclude, I didn't get as far as I wanted, but so therefore the examples I will give you as a homework. So in particular from Brownian Motion, you can already construct many examples, and we'll see that plays how to play around with. We'll play a bit around with them, and then see how these definitions come in. And yeah, unfortunately, we don't see yet why all of this is useful. This will come over the next maybe 1-2 weeks. I hope I didn't bore too many of you. And if there are no questions, then if there are questions, feel free to ask now or later. If there are no questions at the moment, then I would stop now, and we can continue with the exercise session